Everyone. In the previous videos, we have proved that paths and paths homotopy, they can be lifted to unique paths and path homotopies. So now in this theorem, we will prove that if two mappings, two paths are path homotopy, then their liftings, they will end at the same point and they are also path homotopic to each other. So let us state this theorem. Let P from E to B, this is a covering map. And this maps E naught to point B naught of the space B. Now here we will assume that F and G, these be any two paths in space B. From point B naught to B1. And let us say F curl and G curl, these be their respective liftings. Since we have proved that every path is lifted to a unique path. Now here we are assuming PE naught is B naught. So if F and G, they are paths starting at point B naught, then there is a unique lifting F curl at starting at point E naught of this F, and similarly for G, there is a unique lifting G curl at starting at point E naught. So let us assume these will be their liftings uh, in E beginning at E naught. Then now we will prove here that if F and G are path homotopic to each other, then F curl and G curl, they have the same endpoints and they are also path homotopic, because the existence theorem only says that the liftings, they start at point E naught, but that does not tell about where these two paths will end. So in this theorem we will prove that they will end at same point and they will be path homotopic also. So they end at same point and they will be path homotopic to each other. So let us prove this. So now here we have given that F and G are path homotopic to each other. So we can assume F is the path homotopy between F and G. So if this is a path homotopy between F and G, so this is basically a mapping from I cross I to B. So this be path homotopy between F and G. Then what is F00? This will be B naught, because the paths F and G, they have starting point B naught. So F00 will be B naught. Then from the previous lemma, we can say if this is a continuous mapping such that F00 is B naught, then it has a unique lifting F curl, which is a mapping from I cross I to E, and which maps 00 to point E naught. So this is lifting of F in E such that F curl at 00, this is E naught. Now in the previous lemma we have proved that if F is a homotopy, then F curl is a homotopy. So now here F is a homotopy. It means F curl, this is a homotopy. Now if this is a homotopy and it maps point 00 to point E naught, therefore it maps whole of the left edge to point E naught. So F curl maps 0 cross I to E naught. And because it is a homotopy, so it maps right edge again to a one point set. Let us say that one point set is E1. Now if we take restriction of F curl to I cross 0. This is basically a restriction of F curl to the bottom edge of the square I cross I. Then this is basically a path beginning at point E naught, and this is a lifting of F I cross 0. So this is a path in space E beginning at E naught, because now this F curl is a continuous mapping such that F curl at 0, 0 is E naught. And if we take F restriction of F curl on the bottom line, then its domain will be just a closed interval 0 to 1. So this is basically a continuous mapping on the closed interval 0, 1, which is beginning at E naught. So it is a path. And this is basically a lifting. And this is a lifting because F curl is a lifting on whole of the area I cross I. So it is a lifting of F restricted to I cross 0. But we have already proved that the lifting is unique. Now we are saying that F of restriction of F to this I cross 0, this is a mapping who has a lifting F curl restricted at I cross 0, and that lifting begins at point E naught. But we know this path, this has a unique lifting beginning at point E naught. So it means this F curl, which is restriction of this I cross 0, that should be equal to F curl, because F, this basically is equal to F. So this is F, and F curl is the unique lifting of F at point E naught. So this should be equal to F curl. Similarly, we can prove that F curl restricted to I cross 1, this will be equal to G curl, because again this is a path beginning at point E naught because of this is a path beginning at point E naught, and this is a lifting of G, and because lifting of G is, it must be unique, so it is equal to G curl. So from here we can say that F curl and G curl they end at same points, because the F curl at I cross 0, so here because of this reason we can say that F curl and G curl they end at same point, and this F curl is a homotopy between them. So why we can say that F curl and G curl they have same endpoints? Because from this particular part we can say F curl restricted to I cross 0 is equal to F curl means F curl at point S0. This is F curl of S for every S in the interval I. Similarly, from this we can say F curl at S1. This is G curl at S at every point S in I. So from here, we want to prove that F curl and G curl they end at same point. That means we have to calculate F curl at 1 and G curl at 1. So F curl at 1, that will be F curl at 1, 0. And from here, this F curl at 1 cross I, this is E1. So it means F curl 1, 0, this is E1. Similarly, this is F curl at 1, 1. and again it is even. So F curl at 1 and G curl at 1, they are same. So it means F curl and G curl, they have same endpoints. And on the left edge of F curl and G curl, these endpoints are same, and on the right edge these points are same. And F curl is a mapping which is a homotopy between F curl and G curl. So we can say these two have same endpoints and they are homotopic to each other.